Hello everyone, how are you? Can you hear me? Good, great, okay. So before starting the lecture today, I have a question. Did you, so did everybody make the extra midterm, the extra points for the midterm? No, okay, some people is saying no. Okay, not enough time, okay. Okay, from the ones who said no, it means that you didn't have time or you didn't even realize that we had extra points. Oh, okay. Someone is saying, okay, realize something. Okay, so let me just quickly check. Well, I mean, if you were, yeah, if you had the time to try to get the points, and you get there and you were basically confused, that is a different thing, right? SAC. It wasn't the lecture, right? I mean, if you saw the lecture, I mentioned this at the end of the lecture. Okay, so let's do something. Let me give me a second. Yeah, because everybody should realize about this. So give me a second. No, I will not give extra points to everyone. I will not give extra points just for free. Okay, let me check. Give me a second. I'm checking roughly how much people answered this. Okay. It seems that most people did it. Okay, let's do something. I will open it for today. I mean, if really you didn't realize, then yeah, I mean, if you didn't saw the last video yet, and I think we didn't post it on Piazza, so that's my bad. Yes, Zach. At the end of the lecture, at the end of the review one, I mentioned this. But don't worry. Let me open it again. Give me a second. So it will be open. Yeah, basically, if you are hearing this for the first time, it's basically some extra points for your exam. This is basically related with the last questions that, yeah, most people didn't have time to answer. Give me a second. Second. Okay, I'm already open it. So, and because I'm in a good mood today, I will also, I also put 2 allowed attempts. Okay. Okay, I'm saving. And yeah, remember, we will not do this for every midterm, right? I mean, it was just because it was particularly very long and a lot of people didn't have time. Okay. Okay, good. So let's start. So today we have a lot of things to cover, and as I explained on the last lecture, I mean on the review, we will probably need to continue this on an extra video. So, can you see my screen? Good, perfect. Okay. Yes, and by the way, I think Ivo, are you here on the session? Say yes. Okay, good. So yes, so Ivo, can you help me to maybe after this, after the session, post this on Piazza about the extra points,
Okay.
please?
Yeah.
Thanks. Yeah. Okay. Good. So today we need to talk about clipping, rasterization, and we will also talk about a little bit of barycentric coordinates. However, because we will need to talk about clipping, we need to kind of like remember a couple of things from the perspective projection. Remember, I told you that, I mean, we were not done with the perspective projection, right? So let's start. Okay. Good. So these are our learning goals for today. So we need to, again, like revisit a little bit of the perspective projection. I will show you another way to construct a perspective projection, different from the one that is on Shirley's book. That is the one that we saw in the previous lectures. And yeah, remember that in particular, perspective projection is, because it is a complicated transformation, right? It's basically several matrices together. There are different ways to compute that, right? So if you go to I don't know, YouTube and watch some videos or check different books, you will see that in different books sometimes you have different perspective matrices or projection matrices, right? Sorry, barycentric coordinates is very hard. No, it's actually very simple. I mean, I think we will get only a quick view today because I don't think we'll have time. So that will be the part for the extra video. But no. Hopefully, I think the way I will explain barycentric coordinates to you, I think it will be very easy. I hope so. Okay, so perspective projection, again, there are different ways to compute that, right? So we will see today the way you can construct it, the way at least it is constructed in WebGL. And you will see that the final matrix is a little bit different from the one from Peter Shirley's book, right? But it's perfectly fine. And you shouldn't spend too much time on that topic. In the end, it's just a transformation, right? And again, there are different recipes to do exactly the same thing. And yeah, don't worry. Okay, so next we will talk about clipping coordinates, the actual clipping process. And then again, we will revisit a little bit of rasterization very quickly, because inside the rasterization topic, there's something called the scanline algorithm. So we will probably not have time today for talking about the scanline algorithm. And then we'll talk about the barycentric coordinates, which is basically what we use to create this interpolated values when we pass information from one step from the rendering pipeline to another, right? Specifically when we interpolate from the vertex shader, right? The data from the vertex shader to the fragment shader. Okay, so again, let's revisit theoretically or conceptually what we needed, right? So we had information in 3D. We want to convert that information that is already in 3D, into 2D, right? So basically we need three things. We need a camera transformation or eye transformation. We already did that. It was covered on the midterm. We need a projection transformation. Again, we already saw one possible solution for the projection transformation matrix from Peter Shirley's book, and we will see another construction today. And also we need a viewport transformation or windowing transformation. That is basically just like flatten everything, get rid of the set value, and basically flatten everything on the 2D, right? Okay, so let's review a little bit of what we need, right? So this is basically what we need, right? So we have a camera, right? And the camera is pointing to a certain direction, right? And we have a near plane, a far plane. We also have a top plane, right? Right and left. So We already know about that. So basically this is from one side, right? This is basically the frustum, right? So the frustum is this truncated pyramid, which is basically the view area from my camera, right? So the thing is, we have everything in 3D, and this is basically the near plane. It's also called the view window, right? Basically, this represents the image in 2D, right? The image that we need to render in 2D. And if we are talking about perspective, right? Not orthogonal transformation matrix, but perspective, we know that objects that are far, right, from the camera, they need to appear smaller, right? So basically here I have an example of the same object, right? These two objects are basically the same. So in the 3D world, they are basically the same, which means that this vertex in particular, by the way, can you see my mouse? Can you see my mouse? Yes, okay, good. So this vertex in particular is the same vertex, right? From these two objects, right? So what happens here is that what should happen in our perspective projection is that an object that is farther from the camera, its projected point, which is this one, should be smaller than the one that is closer to the camera, right? This is very easy to understand here, right? And so what do you think? What can we do to basically compute this projected version of this point, right, from the one that is farther? Which mathematical tool we already talked about that you think it could be useful? What do you think? Connect the point of the object and the camera. Yes. So somehow this is a vector, right? So this is a vector, and this is basically like the intersection, right? So yeah, someone could say, wow, this could be, I mean, maybe we need the math to compute the intersection between a line and a plane, right? But it's a bit more easy. The thing is, we already talked about this. We need homogeneous coordinates, right? So if you remember, we already talked about homogeneous coordinates. Homogeneous coordinates are this type of higher dimension coordinates that we are actually using. Remember that all our vectors, right, all our positions when we are using affine transformation matrices 4x4, we don't only have x, y, z values, right? So if in the case of vectors, we have a 0 at the end in the w coordinate, and in the case of positions, we have a number 1 at the end, right? So those vectors or column vectors or column points that we are using with 4x4 affine transformation matrices, those are not coordinates in the 3D world. Those are actually homogeneous coordinates in a 4-dimension world, right? 4-dimensional world. It's basically 4 dimensions. And we already talked about that, right? So what is basically the trick with homogeneous coordinates, and again, this was even included on the exam, is that we need to pass from point P, for example, which has x, y, z, and 1, right? These are x, y, z, and w coordinate, remember? So P prime, which will basically the 2D Euclidean version of this, 3D Euclidean version from this 4D homogeneous coordinate, right? It will basically x prime, y prime, and minus 1, right? And the way we do this is basically we take the w value, right? And we just divide every coordinate, right, by the last coordinate from the higher dimensional vector, right? And yeah, you will understand why we have a minus 1 in hopefully in a couple of minutes. But everyone remembers this, right? When we did this on the exam, right? Basically, homogeneous coordinates is always a n minus 1 dimension, right? You take the last value from that vector and basically divide everything else by that value, right? You remember this? No worries. Okay, good. So, give me a second. Yeah, so the thing is, why we need minus 1 here? So remember that when we compute the camera coordinates, the way we compute the camera coordinates is by taking making the Z value from the camera into the opposite direction from the target, from the look at vector, right? Remember that? And again, this is just a convention, right? This is the way we use to compute the camera, or we need to compute the camera projection, the camera coordinates, sorry, in OpenGL. But remember, DirectX uses exactly the opposite, right? So again, this is just a convention by saying which is the sign from the vector that is basically pointing out of my computer monitor, right? So some people think that that vector is positive, right, if it's looking to you, and some other people say, oh no, that should be positive, it should be negative. It's just a convention, right? So in WebGL, we define this Z direction as to be the negative Z direction. And if you remember the homogeneous coordinates, we studied that the homogeneous coordinates is basically projecting every point in the homogeneous space into a projective plane, and that projective plane is basically on the Z value equal to 1. Remember that? And again, if you don't remember, you can go and check that topic again, right? Because we already talked about homogeneous coordinates, and we said that the projected plane is always at the Z value equal to 1. In this case, it's -1, right? It needs to be -1 because we are using this convention from OpenGL that is basically the negative direction from the Z value, right? So if we need to get a -1 here, and I know, right? And I know the way I convert from homogeneous coordinates to Cartesian coordinates is by taking the last value, which is W, right? And basically divide everything by W, right? And I need this guy to be -1. It means that I need this guy, right, to W be -Z, right? Everybody okay here? Okay, good. So by doing that, again, I will go to this image again. By doing that, you're basically taking all the vertices that are already in 3D, and you're projecting those vertices into a 2D plane, which already has these characteristics of having the objects that are far from the camera are basically smaller than the objects that are closer to the camera. So it seems that we've finished, right? It's like, okay, why? So if we only need to take the original coordinates that they were on 3D and basically use homogeneous coordinates, right, to basically create a different version now in 2D that is already taking into account this perspective behavior, right, that objects that are far from the camera are basically smaller, why do we need this freaking horrible and complicated matrix, right? This matrix, remember this matrix? And many people were asking about that. A lot of people were asking, why do we need to take the frustum and basically convert a scale, right? Transform the scale, everything, this frustum into this tiny box. And a lot of people were asking about that. Well, the reason of this is because we need to make the clipping process. And I told you that the clipping process is way cheaper if we first take everything and convert basically everything that is inside this frustum, right? And we convert it into this 2x2 view volume, right? So there are different ways to name this tiny box. So one way to name it is the NDC, the normalized device coordinates. There's also called the canonical view volume, right? So let's see again. So this is why we need this transformation, because we need to perform clipping. Otherwise, we could use only homogeneous coordinates. Okay, so yes, okay. So we need to transfer the frustum into the canonical view volume to make the clipping process easier. Yeah, so that's just the thing I said. Okay, so the perspective projection steps, right? So this weird matrix that I will show you. In the end, it's basically 4 different matrices, right? So the first one we'll do is to move the apex of the frustum to the origin. So remember, we need to convert everything into camera coordinates, and then into like screen space coordinates, right? So conceptually speaking, this is what will happen. The first thing that happens in these matrices, again, conceptually speaking, is that we are basically moving everything, or moving the apex, sorry, from the frustum to the origin. Then we are scaling the z values, right? Basically all the information that we have as depth values, the distance from the camera to every object. We need to scale those values, right, the z values, into a range that goes from -1 to +1. Remember that this tiny box is basically a box that is 2 by 2, and one corner of that box is -1, -1, -1, and the other corner is 1, 1, 1, right? And also in the second step, we basically include something that will allow us to get this division by z. So basically, at the very end of applying the projection matrix to our vectors, we will end up with our vectors transformed, right, with a -z value in the w row, right? And then we just perform the actual homogeneous coordinates transformation, and we'll get everything on the correct transformation. Okay. Then the third step is basically create the perspective calculation. The perspective calculation is this basically scaling everything with respect to the near plane and far plane, right? Remember, the near plane is everything that is closer to the near plane, I don't want it. Everything that is farther from the near plane, I don't want it, right? So basically those are also planes from this tiny box, right? So the near plane will represent the -1 in respect to the z, and the far plane needs to represent the +1 in z, right? And then basically just scale the x and y values, right, in the viewing window to the canonical view volume, basically the last step, right? And again, this is WebGL style, and this is different from Peter Shirley's book. And again, it's not that one is better to the other, it's just different ways to perform the same transformation. Again, remember, transformations are you're very free to perform this type of transformation. And this is this is one. I know at least another way to construct the perspective matrix. Okay, and what do we need? We need this information, right? We need the near, far, top, bottom, right, left. So those are numbers, right? You already saw these letters on the other perspective projection, but this is basically the explanation of what is that, right? So basically near is basically the distance to the near clipping plane along the z-axis, far distance from the clipping plane along the z-axis. And again, these distances here are not with respect to the warp. These are already with respect to the camera coordinates. Remember, the first step was to create the camera coordinates, this -z and all this thing that we created. Remember, we created the coordinate system from the camera, and we basically multiply everything by that matrix. So we remember that, conceptually speaking, instead of moving the camera with respect to the world, we are moving the world with respect to the camera, right? So basically these are distances in camera coordinates, right, from all these planes, right, from the far, the top, the right, the left. Okay, and in particular, right, the top, bottom, and right, left, you will say, well, these are not actually planes, right? These are, because we are talking about perspective, the planes from those top, bottom, and right, left are actually inclined, right? Because this is like a pyramid. So this number right here is basically, again, for example, right, is the farthest right on the x-axis, but on the near plane, right? So it's basically on that, yeah. Let me just quickly go here. So remember, this is the near plane. This is also the view plane, right? So for example, the right, it will be this distance right here, right? So the rightmost coordinate on this plane on camera coordinates, right? And same for top, and so sorry, for right, left, top, and bottom, right? Good. So these are the 4 matrices, and again, explaining the entire construction of every single matrix, it will just take a lot of time, and they're just transformation constructions. So I was I basically reread all the books that we have, and I was trying to get like what is basically where is the probably the best explanation I could find regarding to the construction of the matrix. And I found this web page here. Let me show you the web page. This one is, I think, is very nice. This the one I like the most. Give me a second. So you have the link there, and you can see the entire construction here. And again, this is regarding WebGL, which is basically what you're using, right? So it says it has the entire explanation, but what is also very nice is that it has a real-time simulation of what you're doing here. So you can play with the field of view, you can play with the aspect ratio, with the near, and it basically explains everything from the camera, right? And you can see all the matrices here, and you can modify, right, all the values and see exactly how this is done. And every section is explained, every part of these 4 matrices. In the end, you have these 4 matrices explained. You can even actually click here and basically check like every multiplication, right? And you can basically like follow all the math. So this will obviously take a lot of time for a lecture for us, right? And again, is not as important because the perspective projection is automatic in WebGL, so you will rarely need it. And in the end, these are just transformations, as any other transformation that we already talked, right? So yeah, I think this source is really, really good. And again, remember, I will never ask you to, I don't know, to like prove how do you derive the projection matrix, something like that in an exam. That would be just crazy, right? Asking that on an exam. The type of questions you will get are basically like conceptual questions. That is basically what you need in your computer graphics research career or whatever you need. Okay, so this is basically the first matrix, right? The one that is basically moving the apex of the frustum to the origin. Then we have another matrix that is, again, scaling the z values from the normalized to the normalized -1 and 1, 1. And again, you can find the entire explanation of what are these things are. How do you get these numbers? Oh, sorry, this is wrong. No, this is okay. Yeah, basically this A and B. This is the actual equation for A and B, and yeah, you get these guys here. And this is the one that actually takes the division by z, right? So this -1 is basically we will get this final w into -z, right? To get the homogeneous coordinates later. Okay, and then we have the third matrix, the perspective calculation, which is basically just the near and near, right? And the fourth one, that is the one that is scaling, scaling the x and y values in the window to the canonical view volume, right? So this is basically what happens, right? So we have x, y, z, 1, right? These are original coordinates. These are coordinates that are on camera transformation, camera coordinate system, right? We multiply that vector times all these matrices, right? Which in the end they become in one single projection matrix, right? And we will have this x prime, y prime, z prime, and a w, which, by the way, w will be -z, right? Is the C range inclusive? It is inclusive. The range is inclusive, yeah. And yeah, so this is basically the final matrix, right? And again, if you compare this one to the one from Peter Shirley, some parts are actually similar, some parts are just a little bit different, but this is basically those 4 matrices multiplied together, you get this, and this is the matrix that is computed automatically on WebGL, and that's perfectly fine. Okay, good. So that is what I wanted to show you regarding, give me a second. Yes, so regarding the perspective projection. But again, I'm not as interested in spending a lot of time deriving all these equations. I think is not as important because yeah, it's just a transformation matrix. Okay, good. So Quick questions. Do you have any questions? You want to raise your hand? Yes, Sonam is raising hand.
Hello.
Yeah.
Okay, so two things. So first is, so the intuition I have about perspective projection is you have 8 vertices of the frustum, and what you want to do is go through linear transformations to match the vertices of the frustum to the canonical view volume cubes vertices, right?
That is exactly what you do. Exactly.
Yeah, so why not formulate this as a system of linear equations? Because I think orthographic projection makes perfect sense if you think of it as scaling and stretching.
Yeah.
So in the same way, you can just try to shear the faces of the first term into the unit cube, right? Yeah. So I guess there are like 8 unknowns in your transformation matrices, and there are 8 vertices which you can kind of match. And I believe you can derive the exact same thing by making it just a x equals b problem, and just solve for the a instead of x.
Yes, basic. Yeah, you can also do that. Again, there, yeah. Again, conceptually speaking, the most important thing for me is for you to understand the concept, right? So you said perfectly. The concept is just taking this frustum, right? This truncated pyramid, or the vertices of that truncated pyramid, and basically mapping those or moving those, scaling whatever, to basically match this tiny cube, right? The way you do that, yeah, you can do it with many approaches, right? That's why in different books you find different transformation matrices. So, for example, some people like to use the angle from the camera. They like to use the field of view, but as an angle. So their transformation matrices basically are using like the tangent of the angle and whatever. But again, it's just a different way to construct it, right?
Mm-hmm. One more thing is about the, I guess, output of the perspective transformation is still 4-dimensional, so it's still expressed in homogeneous coordinate system.
Yes.
And then what we want to do is remove W by just removing it from the vector and just dividing each entry by W.
Yes, exactly.
So you're saying that is basically taking the field of view into account, where I guess far objects should appear smaller, therefore the XY values need to scale smaller.
Yep.
Is it something like that? Okay.
And that will happen. And that will happen when you divide by homogeneous coordinate. But before doing the step of the homogeneous coordinates, we will do the clipping, right? So the clipping happens in this tiny box. So not yet on the 2D dimension. Yeah.
Right.
Good.
Okay, makes sense.
Perfect. Okay, good. So let's continue. Okay. Okay, so perfect. So after that, now everything is on clipping coordinates. So that is another name for this tiny box. So again, this tiny box is usually called NDC, normalized device coordinates, or is called the canonical view volume, right? But basically, when you have everything already transformed in that tiny box, right, which is again 2 by 2, the z value is already pointing into the correct direction, at least in OpenGL, and this coordinate is 1. Sorry, this coordinate is 101. This one is -1, -1, -1. This is called the clipping coordinates. You say, now my stuff is in clipping coordinates. Okay. So what is the clipping process finally? So imagine that we have this. We have some geometry. We have 3 triangles inside. Some are inside the box. Some are actually outside. So the clipping process, we already know, is basically detecting which triangles are outside, which geometry is outside, is basically removed, right? So we have something like this: T1, T2, and T3. And T1 is basically inside this box, and T3 is outside, it's clearly outside, right? And T2 is basically in the middle, right? So we have ABC, the points from the vertices of this triangle, and basically this triangle is like trespassing this view volume here, right? So the goal is to basically detect those things, right? So what information do we have? So each clipping plane from this tiny box has a normal, right? And those normals are basically pointing inside the box. And here you will probably begin to understand why it was useful to compute the clipping not in the inclined planes of the pyramid, but in the already 2 by 2 tiny box, right? Because these normals will be super simple in terms of like numerically speaking, right? These are already perfectly aligned, right? And these are basically just 0, 0, 0, 0, 0, 1, 0, 0, minus 1, right? Yeah, so basically the normals are actually easier, and the numbers will be easier to compute. Yeah, so again, each clipping plane, right, has its own normals. So these are the near and far plane. These are right and left, right? So we will use that information, basically the normal, right, and the coordinates from this tiny box and for each plane to compute which geometry is outside and which geometry is inside. Okay, yeah, so this is basically what we need. So this is, imagine that we are seeing the same view but from top, right? And now it's like in 2D. So this is, imagine that this is the right plane and this is the normal, right? And we have a point that is represented, a point that is on that plane, right? The way you construct, one of the easiest ways to construct a plane in computer graphics or in general and geometry is by defining a normal, right? And a point that is basically on that plane. So basically this point will be the center of that plane in this tiny box, and this is the normal, right? So how do we know if something is inside the box, so basically on one side of the normal, or something that is outside of the box, right? Or on the other side of the normal? What do you think? Yes, we will use the dot product, exactly. So if we take, for example, the dot product between this vector, the vector v minus p, right? And we take the dot product with the normal, the result will be negative, right? So it means that it's outside. If it's negative, it means that it's outside. If we take the cross product, for example, sorry, the dot product between now the vector a minus p, which is this green vector, with respect to the normal, right? Now the dot product will be positive, right? It means that it's inside. And here we need to make a small pause to talk a little bit about the dot product, and basically to revisit a little bit the dot product to understand what is the actual meaning of dot products. Okay, because we talk about this like, okay, when do we need when we compute the dot product, when do we need the vectors to be normalized or not, right? So what do you think? Do we need to normalize this vector before taking this dot product? Okay, a lot of people is saying no. Yes. Okay, so maybe, yeah, this will be very fast, right? So what is the geometrical meaning of the dot product, right? So if you see, like, you can see the dot product like this. When you take the dot product between two vectors, in this case, for example, is two unitary vectors, what you're basically doing is by taking the projection from one vector to another, right? So for example, in this case, this vector right here, if this is vector A and this is vector B, and both are normalized, what you have, right, like the value at 60 degrees is basically the length of this vector, right? So a dot product, the geometric intuition of a dot product is basically projecting one vector into another. So if at least one of those vectors is unitary, you can say that the dot product between two vectors, A and B, if A is a unitary vector, the dot product is basically the magnitude of the projection of B over A, right? So it means that, yes, so basically all those things are projections, right? So this point right here, that is the projection of this green arrow into this vector here, is on these coordinates, on y coordinates, is basically at 0.7071, right? And I mean, maybe for some of you this is very, very easy, but you don't know how many people with a lot of experience in computer graphics, I mean, a lot of research experience in computer graphics, I've heard people saying, "Oh, I don't remember if the dot product when it's 90 degrees gives you 0 or gives you 1." that just makes me think that people is just trying to like remember equations, right? But not actually understanding what is the exact meaning from the dot product, right? If you understand that the dot product is a projection from one vector to another, you will never forget that if it's a 90 degrees, the projection is obviously 0, right? Okay. And this is very relevant with the type of constructions that we will use. So after this explanation, I think we all agree with these constructions, right? With distance 1 and distance 2. So d1 is basically the dot product between the normal, right, and the vector a minus p, which is basically this distance, right? It's the projection of this guy into the one that is normalized. You agree? Say yes if you agree. Yes, of course, unless you want to get the angle. But right now, we don't want to get the angle. We don't need to get the angle, right? This is the interesting thing. So in this case, we are using the dot product specifically to take a distance, right? Okay. And yes, and that is the distance because the dot product is just a projection, right? And Mark says, where is the vector measure from? I don't understand your question. I mean, everything every vector is basically starting at 0, 0, 0. So we are measuring with respect to p. In this case, p is like the 0, 0, 0, right? Okay, so everybody agrees with these distances, right? So yes, and I guess you don't have any questions on this, on the meaning of the dot product. Okay, so let's see now what do we need, right? We need to compute this point here. We need to compute the intersection. So the intersection is basically this position right here, right? The point A, plus some distance, right? Plus some vector. So basically the vector b minus a, which is this vector right here, right? If I multiply that vector times a value t, which is basically a scalar, right? I can get into this intersection, right? So basically what we need is to compute t. So you agree with this? That is basically this intersection is this point right here plus this vector, the vector basically I minus a, right? So we need to get this value, right? We need to get the value t, and the value t, by the way, is it needs to be a value that goes from 0 to 1, right? Good. So let's try to construct this. So let's remove p from both sides. So we will have I minus p, it's equal to I minus p plus t times b minus a minus a minus p, right? It's basically this thing. I just I subtracted p from both sides. So let's continue the construction, and now we will take the dot product from both sides. We'll take dot product with n, right? So we'll take now this thing right here, right, the left side of our equation. We take the dot product now with the normal, and we basically do the same with the rest of these things, right? And we will see some patterns here, right? Because do you recognize this thing? What is this thing? N dot a minus p. This thing that I'm showing with my mouse. What is this? Guys, you're not writing. Yes, D1, perfect, exactly. So basically, we can just simplify this, right? And we have something like this, right? This is basically, the dot product between n dot I minus p equal to D1 plus t times D2 minus D1, right? So basically, it's just simplifying this part, right? And what do you think is the result of this guy? The dot product between the normal and the vector I minus p, which is this one. What is that? Yeah, it's 0, right? Because I is also on the same plane, right? So it's obviously at 90 degrees, and obviously its projection will be 0 because it is a projection, right? So basically we have something like this, right? 0 is equal to d1 plus t times d2 minus d1. And if we do our math, we get t, and that's it. This is basically the formula, right? And everybody's happy. So basically, this is how we compute in case of triangles that are basically at the middle, right, in between a plane. This is how we compute the intersection, right? The intersection between those segments with the actual planes from the view, from the canonical view volume, right? And yeah, and by the way, I'm showing only the triangle that is basically in the middle, because we already discussed that the way you compute if a point is outside the volume or inside the volume is just by taking the regular dot product and checking the sign, right? If it's positive or negative, which means that if you have a triangle here and all its vertices have, in this case, for example, negative value, it means that the entire triangle is outside, so you don't care, right? If all the vertices, you take the dot product between those vectors and all the results are positive, it means that the entire triangle, right? It means that it is inside, right? So you don't care about that one, okay? So we only care, again, from the ones that are basically in the middle. Those are the ones that are a bit harder to compute. But this is the math, and it's super, super easy. So once you do that, you basically have something like this, right? You can compute these 2 points, right? So now you can create 2 new vertices, right? So basically, this is what you do. Now you have a polygon. Now this is not a triangle anymore. This is now a polygon. And now we need to triangulate the resulting polygon, right? Remember, I told you this when we were reviewing the rasterization part. These are the last triangles that are actually formed in the entire pipeline. Remember, there are many parts on the pipeline in which we can create new triangles. These are the last ones, but these are not driven by the user, right? So those were the ones from the geometry shader or the tessellation shader. One if n was pointing to the other way. Well, I mean, if n is pointing to the other way, you just need to flip your code, right? Instead of saying, oh, if it's negative, it's outside, you will say, oh, if it's negative, it is inside, right? Yeah, but the convention is always that the normals are pointing inside, pointing into the center of the box. Right now, I don't remember if there is a difference between DirectX and OpenGL. I think DirectX is also defining the normals pointing inside, but I'm not sure. I mean, as far as I remember, everybody takes the math considering the normals pointing inside the box. Okay, so again, now that we have another problem, right? How can we triangulate this resulting polygon, right? So we basically have 2 options, right? We have this option, right, to choose this triangulation, or the option of having this triangulation. What do you think is better? Yes, and someone already said Delaunay. What do you think is better? Having these triangles right here, this one and this one, or this super slim and thin triangle, right? So the result, I mean, it's already on the next page. We usually, the rule of thumb is we usually choose the shortest edge, right? So obviously this edge is shorter than this one. But the reason is because you will say, oh, but it's the same, right? I mean, why is different? The thing is, we usually in computer graphics, we usually try to avoid triangles that are very, very thin, very like slim, because those types of triangles can give us a lot of numerical issues, numerical problems when we are computing things. When we are computing lighting and we are computing different things, those triangles are just problematic. So we always try to keep triangles in something called Delaunay triangulation. So Delaunay triangulation, we will probably talk a little bit about this when we talk about geometry in general. But basically what happens is on this type of triangulation, every circumcircle of each triangle, so this triangle has a circumcircle, right? A circle that is basically fits the entire set of points. Every circle is basically is empty, which means empty means that there are no vertices from other triangles that are basically inside this circumcircle, right? And this is called Delaunay triangulation, and it's also related with Voronoi diagrams. And again, we will probably talk about this later. But for now, you can just remember rule of thumb. The best triangulation is choosing the shortest edge. Okay. So that's it. This is the final result, and everybody's happy and perfect, right? So questions. It's already 50. Yes, Nam, you have a question? Yeah.
Just going back to the clipping part. So this is just my intuition because if you think about the definition of a hyperplane, it's really defined by all sets of points that have the same dot product with respect to the
Yes.
normal, right? So all you're trying to do is just find the barycentric coordinate between point A and point B, and find the t value where the t is a part of the set of all points where the normals have the same dot product. So basically just solving for t such that t belongs to the
Yeah.
surface. Okay.
Yeah.
Yeah, that's just something I wanted to check. Thanks.
Okay. And David also has a question.
Yes, can you go to the previous slides where we do the computation of the t?
Yes. Give me a second.
Yes, I was a bit lost there. I wasn't sure what's t actually is. Like,
Oh,
what's the meaning of
okay.
t?
So check it out. So we need to compute this point, right?
Yes.
Yes. So imagine that the information you have is basically you have point A and point B, right? So this is a vector, right? A minus B, sorry, B minus A is this vector, right? This long vector.
Yes.
So in order to get to this intersection point, you basically need to like shrink this vector to get into this vector here, right? Which is I minus A. You agree?
Okay. Yeah.
By shrinking, I mean you basically need to multiply that vector, the vector B minus A, by some
Or
scalar, right?
something.
If you multiply by 1, you
Yes.
will get here. If you multiply by 0, you will get here. If you multiply by 0.5, you will probably get like around here, right? So t
Okay.
is the scalar. You basically you compute a scalar to get this distance here, right?
Okay.
And
Then
that
why
is
we
t.
need
And that
another?
is t.
Okay. Then why is here another a there, like a plus t, b minus a?
Oh,
Is I supposed to be?
why we are adding
Oh, okay,
a?
okay. I see. Yeah. No. I
Okay.
understand now. Because you need to compute a point, not a vector.
Exactly. Yes.
Yeah.
Yeah, because we want this point, right? So we always need to add
Yeah.
the
Yeah.
origin because remember,
Yeah.
vectors are always starting in 0, 0, 0, right?
Mhm.
Yeah.
Yeah.
Good.
Thank you.
Okay, good. So as I was predicting, so it was a good prediction. After this, yeah, we will have no time to talk too much about rasterization. So basically, we already talked about rasterization. We know this stage basically needs to generate fragments for each triangle, right? And basically assign interpolated values. So the important thing here is how do we interpolate values, right? And again, we already know what is this thing about interpolating values. So what you need is basically you need to define some coordinates for these portions of these triangles here. We need to define some coordinates with respect to the triangle's vertices. This is what you need to basically interpolate values, right? And rasterization, the rasterization is the entire process of taking a triangle that is already projected into these device coordinates, right? And basically define which points are inside and which points are outside. And there's an algorithm called the skyline algorithm, which is the part that it will be on the next lecture, next videos. I told you that I will try to record an extra video. Maybe we'll post it, maybe tonight or tomorrow. And but the most interesting part is the barycentric coordinates, which are basically again coordinates. In this case, for example, imagine that you have a point P, right? And you have 3 vertices from a triangle. So basically, it's to define some coordinates to P, but not with respect to the camera or respect to the world. It's just only to respect to the triangle itself, right? And that is what we will see on next lecture. Yeah. Okay. Good. So thank you, everybody. Remember, we have these extra points for your midterm. I haven't finished the grading for the midterm. I'm keep grading the midterms today. We will probably have the entire grading maybe at the end of the week. And but again, if you are interested in redeem yourself from those last questions about inverse kinematics, please go and do your midterm extra. I think Ivo probably already made the post. Okay. Any other question? Pavel, I don't understand your questions. You're saying your...
Can you hear me?
Yes, I can hear you.
Oh, just wanted to ask you why we calculated the shortest distance. Like, why is it useful to do that? Do we need
That
to
is for
do something with it?
triangulation.
I forgot.
Yeah, basically, after you discard this the vertex, right, the other vertex, and you compute these new vertices, right, you get these intersections. Now you have a polygon that is basically a quad, right? It's not a triangle anymore. Now it's a polygon. But the entire process needs triangles, not quads, right? So basically, you have two options to create new triangles. You either cut the polygon here, and you create this triangle or this triangle below, or you cut the polygon in this direction and you get this triangle and this triangle, right? So what I was explaining is that this solution, the solution that is cutting from A to D, is not as good because you end up with a triangle that is very narrow, and those triangles are very problematic in further computations when we compute lighting and everything, because basically the dot product between these two guys is these are too close, right? So numerically we will have problems.
Okay.
So the rule of thumb,
see.
so the rule of thumb is basically computing the distance from those two possible triangulations or two possible edges, and just choose the one that is shortest. Which in this case
I get it.
Which also complies
Awesome. Thank
with this thing called Delaunay triangulation. Yeah. Okay. Thank you so much, and
Thanks.
I will see you on Wednesday. Bye, everybody. Good question, Ken. Sorry. What if we cut the triangle and get a pentagon instead of a polygon? Yeah, in the end, it can also happen, right? Maybe a triangle can be cut by two planes, right? In that case, it's exactly the same problem. You just need to triangulate a polygon, right? A pentagon, sorry. You need to triangulate the pentagon, and you will need to basically do the same. You will need to compute a triangulation that basically tries to mimic the Delaunay triangulation. Yeah, again, that topic of Delaunay triangulation is more about geometry processing more than computer graphics. Yeah, I mean, it's not as related to this course in particular. It's more from the geometric modeling course from Ala Scheffer. But we will probably talk a little bit about this on our on our geometry lecture. But it's a good idea. It's a good question. Thank you. So what I will do is probably I will try to include that. I mean, your question, like what happens if two planes are basically cutting the triangle. I will include that maybe on the extra material. Thank you so much.